All right, before we move to the last topic, which will be classifying chemical bonds, we're going to just tie up a few loose ends in the unit. We've talked about periodic trends in our previous lesson, and we saw trends in atomic radii, trends in first ionization energy, and trends in electronegativity on the periodic table. There's a couple other things I want you to know, though, before we move on. They're sort of related to those topics. The first is ionic radii. We're not going to really worry about a trend on the periodic table, but rather something much simpler. You need to know that there's two different situations here: cations, which are on the left side of this image, and anions, which are on the right. A cation, you remember, is a positively charged ion. An anion is a negatively charged ion. Cations have lost electrons. That's why they're positively charged. So what I want you to remember is that a cation's radius is always smaller than the neutral atom's radius. So when you lose electrons, your radius will get smaller. Okay, the electron cloud is smaller because you've lost electrons, and therefore the radius of the atom is smaller. So if we were to look at the radii of all the neutral atoms on the left, we'd find that the neutral atoms' radii are larger than their cation radius. On the other hand, if you gain electrons and become a negatively charged anion, when you gain electrons, your radius is going to get larger. So anions are larger than their neutral atoms, and cations are smaller. That's what you need to know. Isoelectronic. Here's a fancy, scary sounding word. It actually means something pretty simple. The prefix iso means the same. So if we have isoelectronic atoms or isoelectronic ions, we have atoms and ions that have the same electron configurations. They have the same number of electrons. Those electrons are just distributed within the same orbitals. So for example, if you looked at a periodic table, and you could pause the video and do this, and find sodium, find neon, and find fluorine. All right, when you're looking at sodium's electron configuration, you'll notice that it's 1s2, 2s2, 2p6, 3s1. If you looked at neon, you'd see it's very similar to sodium without the 3s1. So if you compared Na positive to neon, Na positive means we've lost an electron. So in sodium positive, you've lost the 3s1 electron. What's left would look like the same configuration for neon. In the same way, fluorine is 1s2, 2s2, 2p5, but a fluoride anion, F-, has gained one electron. So now it's 1s2, 2s2, 2p6. And so a fluoride ion looks the same as a neon atom in terms of its electron configuration. So these three atoms and ions, sodium, the sodium cation, neon atom, and fluoride anion, we'd say that they're isoelectronic because they have the same electron configurations. Now notice, although their electron clouds are identical, their nuclei are different. The sodium ion has 11 protons in the nucleus, neon has only 10, and fluoride has 9. So therefore they have different amounts of nuclear charge. The species that has the most protons, in that case it would have been sodium, is going to be the smallest atom, because the sodium with more protons is going to attract its electron cloud more strongly. So neon would be the second smallest, and fluoride, which had the fewest protons, would be the largest of those three. So when you have greater nuclear charge, you have greater attraction for your electrons. That pulls the electron cloud closer. The atom's radius gets smaller. So if you're comparing the radii for isoelectronic species, you realize they have the same electron clouds, but their nuclear charge will differ. So look at the number of protons. The one with the greatest number of protons will be the smallest. The one with the smallest number of protons will have the largest radius. All right, earlier in our discussion of periodic trends, we looked at first ionization energies, and we limited ourselves to discussing the trend on the periodic table for first ionization energies. But we did mention at the time that although there is a first ionization energy, there will also be a second and a third and a fourth until you run out of electrons. The first ionization energy was the energy needed to remove the first valence electron from the ground state gaseous atom. You could take away a second valence electron and a third until there are no more valence electrons. Then, if you want, you can continue taking electrons from the energy level below that, again, until you run out of electrons. So now we're going to talk about successive ionization energies. The word successive just means one after the next. So rather than just talking about the first, we'll look at the first, followed by the second, followed by the third, etc. Okay? So let's take a look at some successive ionization energies. And again, throughout this video, feel free to pause the video to continue taking notes as you need. Here's a complicated looking table, but really let's examine it more closely. On the left, you've got a list of atoms, hydrogen, helium, lithium, beryllium. So this is just starting with hydrogen on the periodic table and moving across all the way to neon. And then it's showing us the successive ionization energies measured in kilojoules per mole. Now is there any, you don't need obviously to copy this down, so don't copy the table down, but let's look for some patterns if there are any in here. Well, first of all, hydrogen has only one electron, so therefore it has only a first ionization energy. So for hydrogen, we are not surprised that there's only one ionization energy. Helium has two electrons, and they're both in level 1. So helium has two successive ionization energies, a first and a second. One thing you want to notice is that the successive ionization energies get larger. So when you go to the second ionization energy, it's greater than the first. Similarly, lithium has 3 ionization energies because it has 3 electrons. 520 kilojoules to 7,000 to 11,800, it gets harder and harder to remove electrons. So you want to highlight the very important point in your notes that successive ionization energies get larger. And the reason for that is because you have the same nuclear charge, the same number of protons, attracting to fewer and fewer electrons. So therefore, the attraction gets stronger for each successive electron, and it gets harder to remove them. Now, is there anything else we can see within all these numbers? Well, take a look at lithium, for example. Lithium, we go from 520 kilojoules. The price for taking away the next electron suddenly jumps, and it jumps after the first ionization energy. It jumps from 500 to about 7,000. Then it goes up to around 12,000. Beryllium, 900, 1,700, and then 14 or 15,000. So for beryllium, there's a big jump after the second ionization energy, a big jump in price. For boron, 800, 2,400, 3,600, 25,000. So for boron, the big jump occurs after the third successive ionization energy. Now you're hopefully noticing a bit of a pattern here. For carbon, there will be a big jump after the fourth successive ionization energy. For nitrogen, the big jump is after the fifth, etc. Now, can you figure out why these jumps are occurring, where they are occurring? So why is there a big jump in ionization energy for fluorine after we took away 7 electrons? Why is it a big jump for oxygen after we took away 6? You could pause the video here and see if you can come up with an explanation for that. If you think of a Bohr diagram, it's relatively simple to explain this here. You have a nucleus. The nucleus has positive charge in it. And then you have an orbit, number 1, an energy level number 1, an energy level number 2, an energy level number 3, etc. What we're talking about here, let's talk about lithium across to neon. So lithium to neon, we're filling the second energy level, right? So lithium had 1 valence electron, beryllium has 2 valence electrons, boron has 3 valence electrons, carbon has 4, etc. By the time you reach fluorine, there will be 7 valence electrons. And then, of course, neon has 8 valence electrons. Now, do you see a connection between the number of valence electrons and where these big jumps occur? If you've got 1 valence electron and you remove it, the next electron that you try to remove will be from an energy level closer to the nucleus, and therefore a stronger attraction, and therefore a much larger energy required. If you had 2 valence electrons, beryllium, then your first 2 ionization energies will increase. You have you've taken away all of the valence electrons after the second, and so there's a big jump when you go to the third. So if you look at it the other way around, if I see for carbon that the big jump in ionization energy occurs after the 4th electron was removed, then I conclude that carbon has 4 valence electrons. For oxygen, the big jump in energy occurs after the 6th electron was removed. Therefore, oxygen had 6 valence electrons. So notice you can tell how many valence electrons an atom has by looking for that large jump in ionization energy. Fluorine, the large jump occurs after the 7th ionization energy. Therefore, fluorine has 7 valence electrons. Here's another way to look at that. From sodium now across to argon, the next 8 elements. Sodium, can you tell from this table how many valence electrons sodium would have to have? Well, for sodium, the first ionization energy 495, the second 4500. So there's a big jump after the first ionization energy. Sodium has 1 valence electron. Silicon, Si, 780, 1575, 3200, 4300. They're increasing in energy, but then you jump up to 16,000. So for silicon, the big jump occurs after the 4th ionization energy, so silicon has 4 valence electrons. Do you see how that data, those measured successive ionization energies, support the idea that electrons have to be found in energy levels, in shells? All right, so when you've depleted an entire shell, there's a large jump in ionization energy. If we were to keep going, we would find that once we used up the next energy level, there would be another big jump until we run out of electrons. All right, so those large jumps in ionization energy show us that the electrons are arranged in shells, in energy levels. Here's one more way to look at it. Here's a graphical representation. Pause the video and see if you can answer these 3 questions on the side. You can talk it over with your neighbor. So what family of elements does this element likely belong to? Well, let's make sure we understand what we're looking at. So this is ionization energies on the y-axis being graphed against number of electrons removed. So the first electron removed here, that must have been a valence electron. Then there's a jump. So there's a small jump here. So that suggests that there was only one valence electron. Let's see if that makes sense. One valence electron, then this guy would be in the second energy level. 1, 2, 3, 4, 5, 6, 7, 8. Yep, that makes sense. There's 8 electrons in an energy level there. Then that level was depleted, emptied, and the next energy level was much higher. The next electron removed was way up here in energy and here. So that suggests to me that there was one valence electron here. That would have been in the third energy level. These 8 electrons here would have been in the level below that, so that would have been the second energy level. And these 2 electrons would have been in the first energy level. So looking at that, we're now getting into the second question here. This would have been 1s2. This would have been 2s2 and 2p6. Those are the 8 electrons in energy level 2. And then this last guy by himself is 3s1. So therefore, this would have been, looking at the periodic table, this would have been an alkali metal, the first column, because it has only one valence electron, 3s1. The describing the electron shell structure, I've done that here. We have 2 electrons in the first level, 8 in the second level, and 1 in the third level. And the element here, well, looking at a periodic table, this must be sodium. 1s2, 2s2, 2p6, 3s1. All right, so hopefully that made some sense to you. Again, the first electron removed was the valence electron. There was a jump, not huge, but there was a clear jump after that first electron was removed, so that meant only one valence electron. Then the next 8 would be from the level below that, and then another big jump. Now the big jump over here is much larger, and that's because you're getting now really close to the nucleus. These 1s2 electrons are pretty close to the nucleus, so the price to remove them is very, very high. All right, see if you can answer this question, and then we'll wrap it up. The first 4 ionization energies for elements X and Y are shown. The units are not kilojoules per mole, but identify elements X and Y. There could be more than one answer. Pause the video and see if you can discuss that with a neighbor. All right, so looking at element X, we notice there's a big jump in ionization energy after the second electron was removed. So therefore, we're predicting that this element X is in the second column on the periodic table. It's an alkaline earth metal. Maybe it's beryllium, magnesium, calcium, strontium, barium, etc. It's one of those elements. What about element Y? Well, it also has a big jump after the second ionization energies. So element Y is also in the second column on the periodic table with 2 valence electrons. It's also an alkaline earth. Can we tell whether or not element X is above element Y on the periodic table, or whether element X is below element Y? We know they're both an alkaline earth metal, but which one's above the other? See if you can figure that out. Pause the video and just discuss that. To answer that question, did you focus on the first ionization energy? X has a lower first ionization energy than Y. We remember from our previous video lesson that when you go down the family, the ionization energies get smaller. Therefore, X is probably, well, it must be below element Y on the periodic table. So I'm looking for X below Y in group number 2 on the periodic table. So this could be this X. Why don't we start with element Y? Y could be beryllium. Could it be beryllium? Yep, it's got 4 Beryllium has 4 electrons, and we had 4 ionization energies here. So Y could be beryllium, and X could be magnesium. Assuming that they're just one above the other, Y could be magnesium and X could be calcium. There's more than one answer. So essentially you had to decide that they're in group number 2, they're alkaline earth metals, because they had 2 valence electrons, and then decide that element Y is above element X because element Y has a larger first ionization energy than X. All right, so that deals with it. That is reviewing a little bit of connections to the previous video lesson, but here we've looked at atomic radius versus ionic radius, and then successive ionization energies.